Okay, welcome back. This is the second video on the dot product. And just as a reminder, u dot v, by definition, um, and we proved this last time, is magnitude of u times magnitude of v times cosine theta. And we often use this to find the angle between two vectors by simply solving for cosine theta, and you get u dot v over magnitude of u times magnitude of v. Just a reminder that on Blackboard, I'm basically recording this off of a PowerPoint presentation. And on Blackboard, I made PDF files. I took 4 slides and put it on a single sheet. They're in color. You can expand them on your screen because it's going to make it easier for you to follow along. You can take notes right on them. And this way, I make sure that what I want to cover is what I cover. All right, so that would be titled Vector Operations 2. And let's get right to it. Okay, all this we covered last time on how we use the law of cosines for that. We did a couple of examples, and we talked about parallel and orthogonal vectors. And we started with this idea of orthogonal projection. This is important. I'm going to make a short video on this because it's not an easy topic, but if you think about it, it's going to make a lot of sense. Okay, so again, an orthogonal projection is a shadow. That's all it is, really. And in this case, let's just look at the acute case for a little while. We did this last time. Let's go over it again. The orthogonal projection of vector v onto a line which contains vector w is this length right here. So this is the orthogonal projection of v onto w. Now, we've seen diagrams like this many times in the past. This is a right angle, so we have a right triangle here. And by definition, cosine theta is adjacent over hypotenuse. So therefore, the cosine of theta is the magnitude of the projection over the magnitude of v. And what we're going to do is we're going to use that idea right now. Okay, so this is the first new thing. So it's orthogonal projections using the dot product. And this is going to get a little bit involved, so this video will be short, and there'll be a third one on another topic shortly. So again, imagine a flashlight casting a shadow of one vector onto another vector. Okay, so if vector v and w are non-zero vectors, with theta the angle between them, then the projection of v onto w equals this. Now, the first thing that you're going to say is, where did that come from? Well, I'm going to show you. It's not that easy, but you can follow it through. All right, so let me read it to you. It's v dot w over the length of w squared. So this is a scalar, right? Dot product is scalar. This is a scalar, so the quotient of two numbers is a number, and it's going to be a multiple of vector w. And notice the projection is a vector, so all we're doing here is we're going to say, what's that multiple of w? Let's go back and look at our diagram. The projection is here. Okay, it's a vector. W is a vector. In general, they are not the same. So the projection, it might be 1.5 or 1 2/3, a double or triple the length of W. That's what we're computing. Okay, so let's go back here. This is the formula, and I'm going to show you where it comes from. Okay, so fasten your seatbelts, here we go. Projection of vector v on w is a vector with length this. Magnitude of v times cosine theta. Now you're probably thinking, how did I know that? Well, let's go back again to our picture. Here we go. Look at the right triangle, okay? And cosine theta is the length of the projection divided by the magnitude of the length of vector v. So that's exactly where we got that from. And then if you solve for, well, let's just take a look at what we got here. All right, so the length, which is the length of the projection, okay, you go back here, it would be v times cosine, right? Theta. So it's the magnitude of v times cosine theta in the direction of w. So this is a length, okay? And what we've got now is we want to change this into a vector, okay? For the simple reason that this is a vector. And we're gonna, to change this into a vector, what we want to do is we want to simply not affect its direction and not affect its length. All we want to do is change it into a vector. So that's like multiplying by a 1. But we have to be careful. We want it to be a vector, so we're going to multiply by a unit vector in the direction of w. And we've done this way many times in the past. This is the definition of a unit vector in the direction of w. Okay, so it's the vector w divided by the magnitude of w. So this is a unit vector of length 1 in a direction of w. So here's the length that we got from over here. Here's the length, and we're multiplying it by 1. This length is a scalar. We want to make it a vector because this is a vector by definition, right? The projection. So this is the length, and we're not changing the length because this has a length of 1. And what we're doing is we're making this thing into a vector in the same line as w. So this is the definition of the projection. Now, it's good, but it could be more useful. And the way we make it more useful is we want to convert it to a dot product. Now, if you think of the definition of a dot product, this is almost it, right? If we wanted to get v dot w, what we would do is what we're actually missing here is we're missing the magnitude of w, right? Because v dot w is going to be magnitude of v times magnitude of w, which we're missing, times cosine theta. So what I'm going to do is I'm going to multiply this expression top and bottom by the magnitude of w. Okay, so multiplying the last line by magnitude of w over magnitude of w, we get this definition for the vector projection of v on w. Let's go back again and see where that came from. If I'm multiplying top and bottom by the magnitude of w, then I'm going to get a magnitude of w squared here. This is unaffected, but the magnitude of w is going to combine here and make this into v dot w. Okay, so that's how we get the dot product involved in the projection. So this makes it much easier to compute. So this is what we're typically going to use. Okay, so we're expressing this in the form of a dot product. Here we go. All right, let's do an example. Let's suppose vector v is 2i plus 4j, and I could have written that in angle iron form by 2 comma 4, right? So 2 comma 4. So this is vector v, 2i plus 4j, and vector w is negative 2i plus 6j. And I could have written that as angle, angle bracket negative 2 comma 6. So minus 2 up 6. So here's angle w, here's angle v. And what I want to do is I want to find the vector projection of v on w. So again, we pretend we have the flashlight. It's going to shine down. Okay, we're going to form a right triangle here, and this outline in green, this length here, is the projection of v onto w. It's the shadow, and the shadow is a vector. Okay, so here's our formula, which we derived on the previous line. Okay, here's our formula, and all we're going to do is we're going to do the computation. And then what I'm going to do is I'm going to look at this diagram and I'm going to say, yes, it makes sense, or no, it doesn't make sense. I think that's always useful. So here we go. V dot W, 2 times negative 2 is negative 4, okay? and 4 times 6 is 24. So you get -4 and 24 is going to give us a 20 on top. Okay, and I symbolize it by this. All right, it's the dot product. I still got my W here. I did the computation. Now, I take the magnitude of W and I'm going to square it. So the magnitude is -2 squared plus 6 squared. So it's 4 and 36 is 40, but it's radical 40, but it gets squared. So I get a 40. So I get 20 over 40, which is a half, times vector W. And if I take half of this, I get -1i plus 3j. So that would be the projection of V on W. Now let's take a look at it. Right here, this green part is the projection. And watch, -1, 3. So this is in fact the vector -I plus 3j. So it makes perfect sense visually and geometrically, and it gives us the same result. It reinforces it when we do the computation using this crazy looking formula, which we're going to write down and use. It's not something we memorize, it's something we use. Okay, so let's go and talk a little bit about vectors in real world situations. Okay, you got a force vector V, which is the force that a child is using to pull his wagon. Now, notice that that vector has a horizontal component, right? That the magnitude of F times cosine theta. We've done that kind of thing many times, and it has a vertical component of magnitude of his force times the sine of theta. And what that means is that the amount of forward motion of this wagon is affected by the x component or horizontal component of his force. And there's also a little bit of a pull because of this angle pulling up, and that would be this force. So what's going to happen in real life very often is we're going to be looking at components, vertical and horizontal components of these vectors. Okay, so we'll come back to that, I think, a little later. And is this the number? Yeah, here are the numbers. Now let's suppose the boy's pulling with a force of 20 pounds. Because of the angle, it's not all directed horizontally, and it's certainly not all directed vertically. Part of the force is directed horizontally, 20 times cosine 30, and part of the force is directed vertically, 20 times sine of 30. Sine of 30 is a half, so 10 pounds is directed vertically, and this is rad 3 over 2 is 10 radical 3 pounds is directed horizontally. So these are the vertical and horizontal components of his force. Same type of thing with the inclined plane type of problem that we've done in the past. And we're going to come back to this in the third and final part of class 17, again seeing how the dot product is going to be used to figure out what these component vectors are. So what we're going to do next time is we're going to concentrate on how to come up with these these right angle or orthogonal vectors that combine to make our force vector. All right, so we're going to see some physical applications, and that's pretty much about it. So again, download Vector Operations 2, because all of these images, all these slides that I've done are on there. So you can go back and view them, and you can look again at how this formula, how we get this formula where this is the length, and that comes, of course, from here, right? Because cosine theta is the magnitude of the projection over the magnitude of the vector v, right, adjacent over hypotenuse. You can go back and look at that carefully, and you'll see that all of this makes perfect sense. Okay, so I'm going to leave you with this, and next time we'll come back and look at part 3. Also short, but it's going to be a little complicated, so you definitely want to print this PDF out. Good night.